What's going on, guys? I welcome you to this video tutorial, and in this video tutorial we'll go through general approach for adder op-amp design for a given output expression. Let's say our question is something like this, wherein the problem statement will be containing the output voltage expression in terms of input voltages, and we are supposed to design an op-amp adder circuit for the given output voltage expression. So how do we tackle this sort of problems? So do we have a general approach? Yes, we do have a general approach for these kinds of problems, and let's go through that general approach first, and later we'll see how to solve this problem.
I'm your Benak Patel, and let's get started.
Now, just by looking at this general op-amp adder circuit, I can make out that it consists of multiple input voltage sources, and I can clearly distinguish between the input voltage sources associated with inverting input terminal with that of voltage sources which are associated with non-inverting input terminal. Voltage sources associated with inverting input terminal are represented in small letters, and the ones that which are associated with non-inverting input terminal are associated with capital V's, and correspondingly the resistances that which are associated with inverting input terminal are represented by small r's, and the ones that which are associated with non-inverting inputs are represented by capital R's. And here small letter m indicates the number of inverting inputs. In a similar way, small letter n represents the number of non-inverting inputs. And here we have Rx and Ry resistances in non-inverting and inverting input terminals respectively, connected to the ground. And along with that, we have a feedback resistance Rf connected in between inverting input terminal and the output. Now, for the given general op-amp adder circuit, we can think of a general output voltage equation as given below, where V0 is used to indicate the output voltage, and the equation looks like this, and you can make out the difference between the V's that have been used in this equation. So the ones that which are associated with capital X are capital in nature. So thereby we are in turn trying to represent non-inverting input voltages starting from V1, V2 till Vn. In a similar way, the ones within the square brackets I have used small letter V, that which are in turn trying to indicate the voltage sources associated with inverting input terminals V1, V2 and Vm. And if I were to go through the coefficients that which are associated with these voltage sources of inverting input as well as non-inverting input, the coefficients associated with non-inverting inputs are associated with capital X, whereas the coefficients associated with inverting inputs are associated with Y. And in fact here, if I add all the X values, I'll be getting capital X. In a similar way, if I add up all the Y values, these are the coefficients. If I add up, I'll be getting the capital Y. So addition is indicated in the form of summation, where I is starting from 1 and we got to add till the last coefficient value. The range is from I is equal to 1 to n. In a similar way, J here is starting at 1 and it's extending till m. And here we have one more value that which we indicate as Z, that which is very crucial in designing the op-amp circuit, and this Z is given as capital X, that which we have got by adding all the X coefficient values, minus Y, that which is got by adding all the inverting coefficient values, minus 1. Value of Z indicates whether Rx or Ry is required in the circuit or not, where Rx and Ry are nothing but the resistances that which are associated with non-inverting input terminal and inverting input terminal. The lowercase variable V are associated with inputs that are summed at inverting input of the op-amp. So here I have used small letter V's, and they are the voltage sources that which are associated with inverting inputs, and uppercase variables V are associated with inputs that are summed at the non-inverting input of op-amp. So here capital V's are used with respect to non-inverting input terminal of the op-amp. And there are three different design constraints when using this technique. And these constraints are scenario 1, scenario 2, scenario 3. Now let's take a first scenario where z is greater than 0. So after calculating the value of z based on xy values, if this z value is a positive value, then Rx will be infinity. So thereby I can leave out Rx in the op-amp design, and Ry value is given as Rf, that is feedback resistance divided by Z, and Ri is given as Rf divided by Xi, and Rz is given as Rf divided by Yj. Here capital R is used to indicate the resistances associated with non-inverting input terminals, and small letter r is used to represent resistances that which are associated with inverting input terminals. And thereby my general op-amp adder circuit would look like this. As we have left out Rx because it's equal to infinity, I have removed the Rx from the op-amp circuit, and here Ry value is given as Rf divided by Z, and Ri values, Ris are nothing but the resistances associated with non-inverting input terminals. This Ri is given as Rf divided by Xi, where I can take on values ranging from 1 to n, where n indicates the number of non-inverting input voltages. In a similar way, I can also calculate resistances associated with inverting input terminals given as Rj equal to Rf divided by Yj, where J can take on values starting from 1 to m, where m indicates the number of inverting input voltages. And in both the cases, Rf is the feedback resistance value. In a similar way, we have scenario number 2, and scenario number 2 is when the Z is lesser than 0. So that is, after computing Z is equal to x minus y minus 1, if the Z value is negative, then we have to consider scenario 2 where Ry is equal to infinity. So thereby we have left the use of Ry here, and Rx will be equal to Rf divided by negative Z, and Ri is given as Rf divided by Xi, and Rj is given as Rf divided by Yj. So here Rx is given as Rf divided by negative Z, and the values of capital R is given as Ri is equal to Rf divided by Xi, and Rj is given as Rf divided by Yj. And we have the third scenario where the value of Z is equal to 0. After computing Z is equal to x minus y minus 1, if I end up with Z is equal to 0, then both the resistances Rx and Ry associated with non-inverting input terminal and inverting input terminal will be equal to infinity. So thereby in this diagram I have left both Rx as well as Ry, and resistances associated with non-inverting input terminal Ri is given as, and the resistances associated with inverting input terminal is given as Rj equal to. So these are the three scenarios in which any given output expression can fall into. And the design approach that which we employ here is, we will specify the minimum value for any resistor R connected to the input of the amplifier, and we introduce new terminology called as Kmax, which is equal to greatest gain of any Xi, Yj or Z. So whichever is greater out of all the three will assign that value to Xmax. Then Rf is given as R into Xmax, where R will be the value that which we can assume, and Xmax is the greatest gain out of Xi, Yj or Z. So whichever is greatest out of Xi, Yj or Z will make use of that value in place of Kmax. Here is a question where they have given the expression for output voltage in terms of input voltages V1, V2 and V3, and they are asking us to design the op-amp adder circuit. So if I make use of the general approach that which we have gone earlier, I can make grouping in this output expression, and I can divide this equation into two groups based on the signs associated with voltages 5V1, 7V2, 2V3. They are all associated with positive sign. So this forms my group 1. Negative 2V1, negative 1V2 forms the other group because it's associated with negative sign. So when I compare this expression with that of my general approach expression, so I can easily make out the coefficients associated with the input voltages for non-inverting input side as well as for inverting input side. So if I do so, clearly 5 will be my x1. I can easily map x2 with 7 and x3 is 2. In a similar way, on the other hand, that is inverting side, I can think of y1 as equal to positive 2, y2 as equal to positive 1. And in order to calculate the variable x, I will be adding all the values of x, where I is starting from 1 to 3 and j can take on only two values. Here n is equal to 3 and here m is equal to 2, where n indicates the number of non-inverting inputs and m indicates the number of inverting inputs. So if I were to calculate variable z, I have to add up the value of x. So in this case so I got to consider the value of x minus value of y minus 1. So that which gives me 14 minus 3 minus 1. So the value of z is equal to 10 in this case. And out of 3 scenarios, I got to consider the scenario where the value of z is greater than 0. Can you guess the scenario? The scenario is the first scenario where the z value is greater than 0 or positive. I got to consider scenario 1. If I do so, Rx is equal to infinity, Ri is equal to Rf divided by Xi, Rj is equal to Rf divided by Yj. So as per the design, we will specify the minimum value for any resistor R connected to the input of amplifier. Keeping that in mind, let capital R be equal to some nominal resistance equal to 5 kilo ohm, and we know that feedback resistance is equal to R into K max is the maximum value in between Z variable, Xi variable and Yj variable, and the value of Z that we have got in this case is 10. So I'll be substituting 10 in the place of Z. The maximum value in Xi is 7. In a similar way for Yj, I'll be considering 2, and out of these three values, 10 is the maximum value. So I'll substitute X1 is equal to 10 and R is equal to 5 kilo ohm. That in turn gives me the value of Rf, that which is equal to 50 kilo ohm. After finding Rf, I can easily go for the input resistances associated with non-inverting input terminal as well as the resistances associated with inverting input terminal Rj. So my R1 value will be equal to 50k divided by 5, that which is our very first quotient, or the value equal to x1. So the value of capital R1 is equal to 10 kilo ohm. In a similar way, for R2, 7 is the x2 value. In a similar way, if I substitute the last value of xi, that is 2, I'll get it as 25 kilo ohm. So these are the resistances. Associated with non-inverting input terminal. In a similar way, I can find out the resistances associated with inverting input terminal as Rf divided by Yj. Yj can take on values 2 and 1. So my starting resistance value is R1 equal to 25 kilo ohm and R2 equal to 50 kilo ohm. In a similar way, I can find out Ry value as Rf divided by Z. Rf value is 50 kilo ohm and the value of Z that which we have got is 10. So the value of Ry is 5 kilo ohm, and thereby I can easily design my op-amp circuit as, so this is my feedback resistance Rf and the value of Rf that we have got is 50 kilo ohm, and because we have got two inputs associated with negative sign, these are the inputs that should be fed to inverting input terminal, and the resistances associated with inverting input terminal are R1 equal to 25k and R2 equal to 50k. So R1 is the resistance associated with voltage V1 and R2 is the resistance associated with voltage V2. So I can think of this as small v1 and this as small r1. Small r1 is equal to 25 kilo ohm. In a similar way, I have to consider another input v2, that which is associated with resistance r2, where r2 is equal to 50 kilo ohm. Along with these two resistances, I got to write the Ry resistance, where Ry resistance is equal to 5 kilo ohm. So this is for the inverting side of the op-amp. In a similar way, for the non-inverting side of the op-amp, I'm having three input voltages. Just by the equation, I can get to know that there are three voltages associated with positive sign, and hence these are the inputs fed to non-inverting input terminal of op-amp. And here we'll neglect the Rx resistance because of scenario 1 where Rx value is equal to infinity. Let's meet in our next class. Thanks for watching.